Ever wonder how your phone magically knows exactly where you are, even if you're in the open ocean? Well, it's not magic. It's GPS, the Global Positioning System, or as I like to call it, satellites politely spying on you 24/7. Specifically, 31 satellites, constantly screaming their location at your phone. And your phone isn't just listening to one, it's actually listening to 4 of them. Well, sort of. At least 4. Usually more like 8 to 12, but we'll stick with 4. Why? I'll explain in a second. Timing first. In order to ensure these satellites broadcast their correct positions, GPS relies on precise timing, like insanely precise timing, because it kind of needs to when the satellites are traveling at 14,000 kilometers an hour. Each satellite has an onboard atomic clock, so accurate it would only lose a second over millions of years. How is it so accurate? Atoms. Come on, it's literally in the name. Unlike regular clocks, atomic clocks use the vibrations of atoms, usually cesium or rubidium, as their tick. Atoms are far more consistent than you in the gym, making these clocks way more precise than any other clock. However, your phone doesn't have an atomic clock, because they're about the size of a fire extinguisher, and ridiculously expensive. Oh, and each satellite has like 4 of them. Try carrying 4 fire extinguishers in your back pocket. Anyways, this is exactly why you need 4 satellites. Just trust me, it will all make sense in a second. But first, let's take a step back. Here's a satellite. It broadcasts its exact location and the exact time it sends the signal. But wait, it knows the time thanks to its overly fancy clock, or clocks. But how does it know where it is? Each GPS satellite is launched into a very specific orbit called a medium Earth orbit, or MEO for short. This MEO is very predictable, allowing ground tracking stations to constantly monitor the satellite's position. These tracking stations watch these satellites like your unemployed friend on a Tuesday afternoon, and detect any changes in orbit. They then update the satellite with its corrected orbit information, but they don't just tell it, hey, you're here now. Instead, the information is predictive. They take the satellite's velocity and position, and use it to calculate a broadcast for hours into the future. The satellite can then consult this broadcast, and its own internal atomic clock, to know where it is at any point in time. Okay, so the satellite reliably knows its exact position, and the exact time, and it broadcasts this information to your phone. What now? Trilateration. Big word, I know, but it's really quite simple. No, I lied, it's really not. Your phone measures how long the signal takes to reach it, and uses this information to plot a sphere around that satellite. It knows the satellite's position because, it won't shut up about it. And the radius of a sphere is calculated based on the speed of light, and the time difference between when the satellite sends its position and when your phone receives that data. After some simple maths, your phone now knows it could be anywhere on the surface of that sphere. Repeat for 2 more satellites, and now you have 3 spheres. Quick geometry lesson for you. 1 sphere doesn't intersect. 2 spheres intersect in a circle, and 3 spheres intersect at 2 points. And your phone is at one of these 2 points, but how does it know which? Common sense. Yep, it really is that simple. One of the points is usually in space, or underground, or somewhere else it really shouldn't be. So your phone is either on a quiet suburban street, or in outer space. Guess which? But wait, I said 4 satellites. So far I've only counted 3. Well, here's the issue. Trilateration requires your phone to measure how long the signal takes to reach it. You may remember that your phone doesn't have a ridiculously expensive fire extinguisher-sized atomic clock, so this calculation probably isn't very accurate. Not good. Don't stress though, because that 4th satellite is here to save the day. Your phone draws yet another sphere around that 4th satellite, and adjusts its own time until all 4 spheres intersect at one point. Oh look, there you are. See? Simple. Just some spheres, atoms, and maths. It's not like we bent time or anything. Oh, wait. Here comes Einstein to crash the party. Ready for some physics? Good. Relativity affects GPS in 2 ways. First, there's special relativity. Satellites move extremely fast relative to us, and moving clocks tick slower. Why? I have no idea. Ask that guy. That means satellite clocks lose tiny fractions of a second each day. Then there's also general relativity. Satellites are far from Earth's gravity, and clocks farther from massive objects tick faster. Why? Ask him again. That means satellite clocks actually gain time compared to ours. Oh yeah, here's the fun bit. The 2 effects don't cancel out. Without correction, GPS positions would drift by about 10 kilometers every single day. And your poor delivery driver will be delivering your pizza to the middle of a lake. Not good. No one likes soggy pizza. If you're curious, general relativity has a bigger effect, so satellite clocks actually run slightly fast. Guess we did bend time after all. But anyways, why should you actually care? Well, because GPS isn't just a blue dot on a map. Banking, airplanes, agriculture, and self-driving cars all rely on GPS. Your life literally runs on these satellites. They give you food, manage your money, and give you directions. They may as well be Jesus. So yeah, next time you feel down, remember that 31 satellites, 4 atomic clocks, and Einstein himself are all working together to make sure you don't die alone in the forest. But hey, subscribe, because if you don't, even the satellites won't be able to save you.